Thank you very much for the invitation. It's my great pleasure to talk about the energy correlators in the multi-collinear limit and some new result at generic scattering angle. Sorry, my cursor is not moving. Okay. So the energy correlators is defined as a correlation function of the energy flow operators when there is energy detectors in this in the collider physics. We can measure a physical observable that is characterized by the angles between any of these detector or directions. And studying energy correlators are important from different purposes. It is key for understanding the conformal-Lyry OPE, and it helps designing novel observables in collider physics measurement at the LHC. And it's also be thought of as a potential playground for novel onshore methods in scattering amplitudes. Because the form of the phase-space integrals for the energy correlators is very similar for the standard Feynman representation for Feynman loop integrals. And the loop integration techniques can be applied for analyzing these type of integrals. Today, I'm going to be discussing a very specific topic, which is the integral that is emergent in the endpoint energy correlators at tree level in the multi-collinear limit or at any generic scattering angle. As you will see later, such observable will define a phase-space measurement that tells you the integration domain is in the interior of an n-1 simplex for endpoint energy correlators. And this integration contour intersects the singularity surfaces that are either degree 1 or degree 2 in the integration variables. In the most simple cases, these integrals can be directly mapped onto one-loop Feynman integrals, namely the n-gon in n dimension. In the less trivial examples, some methods for analyzing in the Feynman loop integrals, for example, projective geometry, can also be applied to develop a novel approach for calculating the endpoint energy correlators. In addition, such integrals are very special because they correspond to finite physical observables, which also give us some handles for analyzing it in an efficient way. Let me first start by defining the phase-space integrations for the endpoint energy correlators at leading order. A leading order, what we mean is that you're measuring, for example, the energies of the three particles, and you're fixing the angles of the three particles, and in certain directions. However, there is a fourth particle that is not measured, and you need to integrate over all the onshore degree of freedom in the four-body scattering phase space. And therefore, you need to integrate over the energies E1, E2, and E3 for the particles that goes into your detectors. And however, the last particle, number 4, needs to be on shell, and its energy needs to be positive. This defines a hyperbolic surface parameterized by your integration variables E1 through E3. And these energy variables are treated as coordinates on the hyperbolic surface. And the positive condition for these energy parameters tells you that the integration domain is in the interior of a triangle that lives on this hyperbolic surface. And for each point in this triangle, you can be represented by a projective line intersecting the origin and its point x star, which then projects this point onto a canonical n-1 simplex, which is a triangle in the flat space. Therefore, you can write the integration measurement function as a projective integral, which will parameterize by these projective coordinates. And the integration measurement will naturally contain as a quadratic terms, which are defined by a n by n matrix. However, there is a simplification when you take the multi-collinear limit such that you can send all the angle parameters goes to 0. In this case, the onshore phase space integration measurement is the standard measurement for the canonical simplex delta n-1. Therefore, the integrals that emergent for the endpoint energy correlators takes the same form as for the standard Feynman loop representation for loop integrals. So far, I have only been discussing the phase-space measurement, but I have never mentioned the integrand for the endpoint energy correlator, which encodes the physical singularities. For the generic angle, if you study generic angle, then the endpoint energy correlators is given in terms of the n+1 point form factor squared, Fn plus 1 squared, which is defined in terms of the half BPS operators in n=4 super Yang-Mills theory. And the integrand will contain singularities which are either degree 2 or degree 1 in the integration variables, which are the omega 1 through omega n, namely the energies of the n particles. And it can be written in the form that it's either homogeneous degree 2 or a mixed degree 1 and degree 2 polynomials. In the multi-collinear limit, when all the angles goes to 0 and all the singularity becomes either homogeneous degree 2 or degree 1, which is will greatly simplify. And here we can see that the final analytical result will depend on the angle variables theta ij, which are defined in terms of 1 minus cosine theta ij. And you can parameterize these angles by the coordinates on the celestial sphere. If you're measuring three angles, and these directions of the three energy detectors will be mapped onto 3 points on the celestial sphere, which is then parameterized in terms of two independent angles, tau 1 and tau 2, and a parameters S, which characterize the radius of the circle where the 3 point is sitting on. So in the multi-collinear limit, a lot of studies have been done for these integrand for the energy correlators, which are given by the 1-to-n splitting function. These integrands, Gn, can be obtained either by taking collinear limit of the form factor squared or by taking collinear limit of the n+3 amplitude squared. So in the case where n=3 and n=4, we wrote down this integrand in terms of a dual conformal invariant cross ratios, define a periodic dual coordinate space. And the Gn is obtained up to n=11 in a recent paper by Professor He by taking the collinear limit of n+3 amplitude squared. And here in this integrand, you can see that all the singularities are either degree 2 in homogeneous degree 2 in terms of the energy variables xi and xj, which are parameterized by the angular separations zij squared. Or this is simply the linear terms, which is the sum of the energies in the collinear group. And therefore, the integrand is either factorized in terms of degree 2 and degree 1 singularities. And here we have obtained the analytical results for the 3-point or 4-point energy correlators in multi-collinear limit. And these are polylogarithmic functions parameterized in terms of the coordinate of the energy detectors sitting on the celestial sphere. So for the n=3 case, the 3-point energy correlators is parameterized in terms of one pair of complex variables, z and z bar. And for the n=4 case, it is parameterized by the 4 variables, z, z bar, and w, w bar. And the analytical result has also been obtained for the n-point energy correlator for n up to 4 in the generic scattering angle. In the case where there were only 2 detectors, the EEC was obtained by an off-shell approach by integrating discontinuities of a 4-point correlation function. And for the n=3 and n=4 case, we recently obtained these computations and obtained analytical results for all the master integrals by the method of IBPs and differential equations. And in the case where n=4, we can see that the final result is no longer multiple polylog, but it also contains 3 type of elliptic curves, which I will show later. So in this talk, I will introduce the method that we applied for doing these calculations. And for the first part, I will focusing on integration by part plus differential equations for finite integrals algorithms. And these algorithms can be directly applied for such integrals in Feynman parameter space. And the algorithm apply both to calculations in multi-collinear limit and at generic scattering angle. And after having this algorithm, we obtain the energy correlators written in terms of minimal set of finite integrals, which are the master integrals. Having this information is very important for us to analyzing both the energy correlators in n equals 4 and in QCD. Supposing in QCD, you already know what the master integrals look like, and then remaining obstacle will be determining the rational coefficients Ci in front of these master integrals Bi. Then we developed a shortcut approach for determining the rational coefficients. The idea is the following. Suppose we already know the highest weight coefficients, then we can, by a certain approach, then we can bootstrap the lower weight functions from physical constraints, namely the spurious poles must cancel between the highest weight and lower weight functions. And therefore, the task would be to determine the highest weight coefficients. And we find we can apply the spherical contour algorithms in the paper given by Nima and Alice in the 2017 paper. By taking higher sequential discontinuities on the integrand, we can now extract and determine the highest weight coefficients Ci, and then apply the semi-bootstrap approach so that we can determine all the lower weight rational coefficients. And this algorithm applies for the energy correlator in multi-collinear limit, and it still has a potential to be developed and generalized for the case of generic angle. So first, I will go very briefly on the IVP and differential equation algorithm that we developed for calculating the NENC. And everything I speak here will apply both in the collinear and at generic scattering angle. So first of all, you will need to write down the integrations, the integration topologies. And for example, for the 3-point correlator in the collinear limits, and the integrand is simply given in terms of the sum of 3 cross ratios, U1, U2, and U3. And then you can write down your integral topology, which contains 4 types of denominators. 1 is a quadratic, and 3 are linear terms. And in the case with 4-point energy correlators, you can similarly write down your integral families, which can contain up to 2 quadratic denominators at one time in a single integration family, and a set of linear denominators combined with the quadratic. And in order to take advantage of the fact that these integrals are finite integrals, which define physical measurement, we need to guarantee that all the differential, all the IBP identities only involve these finite integrals, not the one that can potentially diverge. Therefore, we apply the power counting conditions on the differential IBP differential operators as well as the integrand, such that we make sure that all the IBP identities that we generate will involve only finite integrals. And since we're doing the IBPs in integer dimension, and we will need to take into account the boundary terms that emerge on the codimension and 1 boundaries of the integrals that we deal with. And in recent work, we have updated this algorithm such that we incorporate the CCG equations approach. Namely, we can write down the CCG equation to constrain the IBP operators that we write down. We obtain the IBP operators such that any denominator dj that could potentially vanish are not increased, are not doubled or tripled by the differential operator that's acting on it, so that we can make sure that all the IBP identities that we write down are safe and does not involve divergent integrals. So in addition to that, we also lift this IVP algorithm to differential equations by adding a differential operator acting on the angle parameters to the IVP operator. By solving these the CG equation, incorporating both IVP and the differential operators, we can derive a finite differential equations for the mass integrals, which takes a block triangle form for the UT basis. In the case where n equals 3 in the collinear limit, the integral families given in this graph contains 5 mass integrals, and their transcendental weight are graded. And you can just read off the symbol alphabet by looking at the differential equation for the pure mass integrals. And at generic scattering angles, the problem becomes much more complicated. For n equals 3, you need to consider 3 different families. Each contains 3 types of denominators, which involve 2 types of quadratic denominators. And for the n equals 4 case, at generic angle, there were 13 propagators in total and 141 mass integrals. And we have obtained an analytical result for all the mass integrals in n equals 3 and n equals 4 case. And in the n equals 4 case, at generic scattering angle, the result is given in terms of absolute weight 3 and PL functions, as well as 3 type elliptic curves, which are emergent whenever the integrand contains 2 different kinds of quadratic denominators. So in the next part, I will discuss how to obtain the IVP coefficient efficiently without doing the heavy IVPs. This algorithm is applied to the case where in the collinear limit for 3-point and 4-point energy correlators. So let us have a look of these at these integrals again. So in the n equals 3 case, in the collinear limit, the E3C is given in terms of a threefold integral over a simple rational integrand. And the third term has no kinematic dependence, which we can put it aside. And the first term and second term are symmetric by a flip symmetry. Therefore, we can only just stare at the first term. So we decided to apply the method introduced by this paper by introducing 2 more Feynman parameters such that we combine all the factorized denominators into a single quadratic, which is parameterized by 5 Feynman parameters, x1, 2, 3, which are the energies, and x4, 5, which are the additional new Feynman parameters that we introduced. So that this integral, well, the integrand is given here, is written in terms of rank 3 pentagon integral, which is denoted by E5, 3. And the quadratic denominator Q5 defines a 5x5 matrix, which are parameterized by the 2 independent angle parameters, U and V. Applying the algorithm in the Nima and Alice paper, we can write the tensor integral, the pentagon integral, in terms of a derivative hitting on external kinematic parameters U and V on the rank 1 tensor integral, so that we lower the rank of the numerator. And then in addition, we can write the E5, 1 in terms of exact form so that the integral is localized onto the codimension 1 boundaries. In the end, we obtain an extremely compact form for the 3-point energy correlators, which is given in terms of first-order differential operator, partial U times U plus partial V plus times V, acting on a set of 4D box integrals. And each integrals is characterized by a 4x4 quadratic matrix Qi. And it is a pure function by definition, and is given in the quadratic that characterize these box integrals can be read off from the pentagon quadratic by deleting row and the ith row and ith column. And so in this way, we arrive at the final expression for the three-point energy correlator. In terms of derivative acting on a set of finite 4D box integrals and the two additional terms that has no kinematic dependence. These are all motor integrals, and they evaluate to weight 2 and weight 0 constants. So in this way, we can see that there is in total 6 master integrals in the problem, and all of them are finite. The first one is a linear, particular finite combination of 4 divergent box integrals. So here we can see that the box integral has massless internal propagators by definition, and it has contains one massless external legs or 2 massless external legs. But you can verify by converting these integrations into momentum space that collinear and soft divergence will cancel among on the 3 integrals, and it is a finite combination. And this combination we call B1 is evaluated to a weight 2 polylogarithmic functions parameterized by the variable u and v. And this is exactly correspond to one of the UT mass integrals that our IVP algorithm discovered. And the second mass integral we call B2 is a 4-mass box with zero internal mass, but it has 4 optional legs, and it's a finite on its own, and it's evaluated to the Bloch-Wigner dilogarithms. And then there was two lower weight 1 function, which is derivative acting on the 4-mass box. And then there was 2 constant terms, which are given by the Armoto integrals. They are evaluated to zeta 2 and 1 respectively. So what do we learn from this exercise is that there is a hidden relation between the highest weight and lower weight rational coefficients for the energy correlators. They are not completely independent. For example, if you do the naive integrations and you could obtain the final answer for sure, but then you can see that the weight 2 piece is multiplied by a rational function z minus z bar to the power of cube, so that you can see a spurious pole at z minus z bar. However, you know that such an unphysical pole cannot appear in the final result. Therefore, the lower weight function must also contain such a pole, and it cancels with the pole that you obtain from the highest weight functions. This is just a simple example that shows that you can use such physical constraints to determine the lower weight rational coefficient Ci once you already know the coefficients that sits in front of the highest weight functions. Therefore, we come up with an algorithms, and then the idea is the following. We need to compute the symbol of the highest weight functions by taking maximally iterative sequential discontinuities on the integrand, and so that we can fix all the highest weight rational coefficients sitting in front of our mass integrals. And then we impose physical constraints, and imposing that all the spurious poles must all cancel so that we can fix all the lower weight coefficients. And this is how the algorithm looks like. And the workflow is the following. The first, we write down the integrand, and in QCD, and it is the integrand will be much more complicated. And then, since we already know, assuming that we already know all the master integrals, we do not need to do the IVP reductions again. However, we will use Feynman parameterization to combine all the propagators and put the integrand in a standard form. And then we apply the spherical contour algorithms to extract the highest weight symbols and compute the rational coefficients sitting in front of the highest weight transcendental functions. And then we use physical constraints by imposing that lower weight functions must cancel all the spurious poles that you see in the highest weight functions. So the first step is to extract the integrand. And for n equals 4, we already showed what the integrand looks like for the case where n equals 3. And for QCD, and this splitting function was also obtained in literature, and we need to consider the splitting function for quark-jet and for gluon jet separately. And then we write the integrals by combining all the denominators into a single quadratic terms. So it is always doable for 3-point energy correlators in collinear limit because the integrand contain only a single quadratic as 1, 2, 3. So then by introducing more Feynman parameters, you will not increase the degree of the singularity curve. And all the integrals can be combined into a single quadratic. And for n equals 4, where there were 4 particles that goes collinear, the integrand contains several different types of quadratic denominators. In certain cases, you can still introduce Feynman parameters in a way that it does not increase the degree of the singularity curve and keeping the term, the denominators degree 2. For example, if you have a quadratic as 1, 2, 3, 4, and another one as 1, 2, 3, the difference between these quadratic factorized in terms of 2 linear terms, so that you can use the projectiveness of the integral and do and pick a certain choice of Feynman parameterization, so that you can combine these 2 quadratic into a single one. And for these cases, we need to introduce at most 7 integration parameters to combine all the integrands into a single quadratic. And these integrals will be reduced onto 60 hexagon integrals, which is maximum weight 3. But there is additional terms coming from different integral topologies that contains, for example, S1, 2, 3 and S2, 3, 4. And these 2 quadratics cannot be combined together and play a trick, as I just explained here, into a single quadratic. By introducing a Feynman parameter t and combining these integral, the 2 quadratics, the denominator will be intrinsically degree 3 and it will be a cubic curve. Therefore, in order to still apply the spherical contour algorithm, which only apply to quadratic denominators, we need to keep t as a deforming parameter, which will be treated as a parameter at the current stage, but we will integrate over t in the very end after we have already extracted the symbols for the highest weight functions.
5 minutes.
So this, sorry,
My turn.
5 minutes.
Yeah. 5.
Thank you. Okay, thank you. So this is how the algorithm look like to summarize. So we apply the algorithm of the spherical contour by reading off each entries of the symbol from the n by n quadratic matrix Q. And it is given explicitly and in the paper by Nima and Alice. And for the first entry, we can read off from a 2 by 2 submatrix from the inverse of the matrix Q. And then we extract the discontinuities by integrating over a spherical contour. And then we obtain a new integral, which is still a quadratic integral, but contains n-2 Feynman parameters. And iterating this procedure, we can read off all the symbol entries and determine the rational coefficients sitting in front of these symbols, which is the coefficients that we aim to obtain. So in practice, we need to deal with not only scalar integrals, but also tensor integrals, which has a certain rank on the numerator. So the algorithm still works very well. After in each step, we pick one pair of Feynman parameters, xi and xj, and then we do a transform and putting the quadratic in such a form. And doing so allow us to project onto a subspace, which is as formed by omega I and omega j, and then we pick a spherical contour for omega I and omega j. And this S2 spherical contour will allow us to extract these discontinuities associated with the symbol entry that I just displayed in the previous slides. And in more complicated situations, the integral itself, is a mixed weight integrals, and the spherical contour algorithm naively only extracts the maximally iterated discontinuities, and it tells you what the leading weight symbols look like. And in order to extract lower weight symbols, we need to first calculate the leading weight symbol and then subtract off the leading weight contribution from the original integrand. And then we do the calculation again so that it will give us a lower weight symbol. And this algorithm is still very computationally intense if we do it in this way. However, if we only aim at extracting the rational coefficients of the symbol at maximum weight, it is highly efficient. And for determining the lower weight, we can use the bootstrap approach, as I explained earlier. So then the strategy would be to bootstrap the lower weight coefficient. For example, this is just a simple example that contributes to the 3-point energy correlators. And the highest weight symbol looks like the following. This is obtained by the spherical contour algorithms. Although this integral has a rank 2 in the numerator, the algorithm is still very efficient in computing the highest weight symbols. And then in order to determine the lower weight contribution to this integral f1, we will assume that the spurious pole that we see here, z minus z bar to the power of fifths, will all cancel, so that we can write down the ansatz that is a function of a rational function in terms of the angle parameters z and z bar. And the ansatz contains all the lower weight functions, symbols of the master integrals, which are given by a logarithm z times z bar and a log of the 1 minus z times 1 minus z bar, and also a weight 0 constants. So just by imposing that the physical constraints that all the higher poles at z minus z bar equals 0 cancel, we can fix all the coefficients in our ansatz and completely determine the symbol that contribute to these physical integrals, contributing to the 3-point energy correlators. And we're now applying this algorithm on the study of the QCD results. And it also, we also see the preliminary result, and that the algorithm goes through smoothly.
2 minutes.
Yeah, and in the last slides, I will discuss the future outlook by applying this algorithm to the 4-point energy correlators in the collinear limit. As I briefly mentioned, the algorithm will work very well when there is only a single quadratic terms on the denominator. But whenever there is a degree 3 singularity curve, it will no longer work. However, we can always treat one of the Feynman parameters t, for example, as a deforming parameter. At this stage, it is treated as a kinematic parameter, but we will integrating over it in the end. For example, this integral can be written in terms of a deformed box integral, and is given in terms of weight 2 polylogarithm function depending on this deforming parameter t and the angle parameters zz bar and ww bar. But the leading singularities in terms of this box integral will be a determinant that you can read off from the original 5 by 5 quadratic matrix, and it is degree 3 in the deforming parameter, which tells you that the final result to this integral will be contain cubic root, which depends on the angle parameters. This is the essential difference that makes it more challenging to analyzing the 4-point energy correlator by our method. And in the future, we're trying to generalize our method onto analyzing the ENC and generic scattering angle. And a generic angle, the integration contour will no longer be a canonical simplex, but a simplex sitting on a hyperbolic space. and there will be complications coming from the irregular boundaries, as well as multiple conjugate denominators. And we hope to apply a generalized projection approach and combine with symbol calculations from projective geometries for understanding these integrals. And our final goal was to understand how to bootstrap the QCD results by all the the knowledge that we have already gained in the calculation in course 4. And also we can also hope to generalize the algorithm to higher loop energy correlators, which will contains infrared divergence. Therefore, it is very essential to build a regularization scheme such that we can still apply the algorithm that applies to finite integral defining n dimension. Therefore, if we can still define the phase-space integral with cutoff in n dimension, we can still hope to apply the algorithm for the higher loop energy correlators. Thank you very much for the attention. That concludes my talk.
Julio? Sorry. My bad.
Okay, thanks for the nice talk. I just have some basic questions. One is there a possibility that you can have a spurious cut that you have to cancel, or just both?
Sorry, spurious cuts. What do you refer to?
Cut that is not physical.
The z equals z bar is not a physical singularity. The physical singularity corresponds to the case where two detectors go collinear, for example, so that z and z bar goes to 0 or goes to 1 simultaneously. But z equals z bar is not a physical singularity.
But this function has branch cuts, right? These functions you compute, or just both? In general, it has branch cuts.
Yes, it has branch cut by a spurious pose. I'm only referring to the rational coefficients at the high degree pose in z minus z bar. So are you saying that there could be a log in the z minus z bar?
In general, right? I mean, just...
Yeah, it could be, but it doesn't affect the argument here. The argument is that whenever you see a higher degree pole, 1 over z minus z bar times a transcendental function, and it cannot appear as in the final answer because there cannot be a pole sitting at the z bar.
That it was no cuts, like a cut that would not be in the physical region or something like that. Yeah, anyways. And the other question was about, so there's a last rational piece which you cannot fix, right? Like a constant that doesn't multiply any integral? Or is it, how do you...
We could fix the constants, the rational coefficients for the constant piece, because it also potentially contributes to the unphysical pole, z minus z bar to a higher power, for example.
If I have like an overall constant, you cannot fix that, right? Like a plus a constant.
You mean it's an overall constant that does not multiply any pole?
Yeah.
Is that what you mean? So whenever there is a term that is not multiplied by a pole, we can fix it from other physical constraints. For example, the collinear limits where when the z goes to 0, z and z bar goes to 0, or z and z bar goes to infinity, or z bar goes to 1. So these are the three physical regions that we consider. So this gives you 3 different constraints. So for the constants, well, it strictly cannot appear because the limits where z and z bar goes infinity must go to 0 for this specific integral.
Yes, thanks. Yeah.
Unfortunately, because of time, we have to move on. So let's send Kyle again.
Thank you very much.